Simulations are virtual worlds where you can instrument each vehicle to track its location, compute its travel time, capture its speed, or measure its emissions. Governments, research institutes, and companies use modeling to test the impact of transportation policies and get results that are accurate, measurable, and easy to compare. The scope of testing is virtually unlimited. It can include private vehicles, HOV lanes, congestion pricing schemes, clean air zones, public transport, dedicated bike lanes, human and AI-driven vehicles, pedestrian crossings and zones, motorcycles, car sharing, and more. Most importantly, once you've set it up, testing costs a fraction of any other modeling method, let alone real-life implementation. Let's take a look behind the scenes at the process of creating these platforms. 1. Import the road network. Our technology supports most commonly used platforms, including GIS files, OpenStreetMap, and aerial photography. 2. Checks. Our team reviews and fine-tunes the geometry and rules using a combination of satellite imagery and local knowledge. 3. Add the public transport schedule. This is a simple import of a GTFS file, followed by quality control tests to make sure everything is okay. 4. Add signal and sign information. You can import raw information from the city via scripts or synthesize signal cycles for quick testing. We make the models as lifelike as possible. Once we've taken care of the supply, we need to look at demand. To understand what trips travelers want to make, we might use cell phone data or modeling from ground up to identify which zones are attractive, at what times, and why. We then apply powerful models that mirror a traveler's search for the quickest route to a destination, while taking into account all of the operational conditions. When a model run is over, you can see the results in easy-to-understand graphs, temperature maps, comparison charts, and powerful animations. Let's look at a few examples. New York City has one of the busiest and most complex transportation networks in the world. Modeling challenges include on-street parking, tunnels and bridge operations, speed enforcement, transit signal priority, pedestrian volumes at key intersections, and congestion relief schemes, such as Midtown in Motion. Our platform has informed every major transportation decision in the last decade, from the pedestrianization of Broadway to the recent rehabilitation of the Brooklyn-Queens Expressway. Our Paris model is as huge and complex as the city itself. The multi-level model combines huge scope with great detail and has been the bedrock of the city's transportation planning and operations for nearly a decade, from remodeling the entire Eiffel Tower area to integrated mobility schemes in Bastille Square. To help implement clean air zones, the London emissions model was developed for Transport for London and integrated into Aimsun Next. Now you can visualize and compare carbon dioxide and nitrogen oxide emissions from configurable fleets of vehicles, including electric vehicles. Another UK study on air quality used satellite-generated atmospheric data to help local authorities in the city of Leicester devise real-time traffic management strategies for reducing pollution levels. The 400 series highway system in Toronto is the second busiest in North America. The model has been instrumental in deploying and configuring hot lanes and was key to a successful Pan Am Games. By comparing congestion levels and travel times pre-game and coming up with tested operational strategies, the team successfully ensured that spectators and athletes alike got to their destination on time. In more than 80 countries worldwide, our mobility models guide decision-making so that safe, affordable, and clean systems of transport are available.